So the next speaker is Giulia Varotto from the Fondazione Carlo Besta. And she's going to talk about localization of the epileptogenic zone in focal epileptic patients, comparison between inter-ictal EMG and stereo EEG network analysis. So thank you, Giulia. The stage is yours.
Thank you. And first of all, thank you for organizing this very interesting workshop. And also thank you for all the people who still are here at Friday afternoon. So thank you to remain and follow the next presentation. So as was introduced, I would like to present a methodological tool that we developed in order to support the localization of the epileptogenic zone and compare the application of this method to both two signals, stereo EEG intracranial recordings and MEG recorded on the same patients. So I will repeat some concepts because I saw that other people talk about focal epilepsy and surgery. But anyway, we know that we are moving in a framework of kind of epilepsy that account for more than 0.5% of all epileptic patients, and a percentage of these patients are resistant to any anti-epileptic drug. So epilepsy surgery up to now is the only chance to treat this kind of epilepsy, this percentage. And despite the huge amount of techniques and research, the precise definition of the epileptogenic zone still remain an open question. And this can be seen also from the quite high rate of failure that we can see after surgery. So about 30–40% of patients still are not seizure-free after surgery. And this percentage is mainly and is higher for extratemporal lobe epileptic patient and patient with non-lesional MRI. That are the kind of patient that we will work with and we will present in this work. So as we saw in these days, different signal processing can be a useful tool to increase and support the correct localization. Nowadays, stereo EEG still represents the gold standard method, but it has some main pitfalls. It's invasive, very long recording time, and the need to record ictal activity and several seizures, and also the subjectivity and time-consuming analysis to localize the epileptogenic zone that still remain in the clinical procedure a definition made by clinical subjective observation. So there is always a growing interest in find equivalent with non-invasive surgical localization approach. And we know that MEG already proved to be efficient for localizing the epileptogenic zone, but or to correlate somehow with the epileptogenic zone. But most of the work, we can say, is based on the localization of inter-ictal epileptic form discharge. But we know that already is very well known that epilepsy is a brain network association, and that also focal seizure is not so focal, but involved a complex interaction and network of different regions that are not only the close and proximal regions. So, and moreover, we know that while most of the investigation focus on identified altered connectivity and network during inter-ictal state, and that most of the evidence to localize the epileptogenic zone based on network analysis are connected to ictal events, we also know that this kind of alteration are already present in inter-ictal state and not only strictly related to the epileptogenic spike. So, and moreover, and these evidence are already present, but most of these are based on MRI-extracted connectivity and also are mainly limited to the temporal lobe epilepsy. So what was the aim of this study? We wanted to focus on the analysis of inter-ictal network analysis on of signal coming both from stereo EEG and MEG of the same signal of the same patients. The signal were not co-registrated, but were acquired closely in time from the same patients. And we wanted to implement it, a completely automatic tool able to localize and classify the epileptogenic zone based on inter-ictal network information. So we had 18 patients with different etiology and different epileptogenic zone localization, divided into two groups. 10 of them were seizure-free after 3 years of follow-up, and other 8 were not seizure-free. And all of them we had negative MRI, so no lesion visible to MRI scan. We consider only 3 minutes of inter-ictal stereo EEG and MEG EEG in eye closed and awake condition. What we did to compare this signal, we consider the stereo EEG, and for the MEG MEG, we reconstruct virtual electrodes, so source analysis of MEG, considering the anatomical coordinates and location of the corresponding stereo EEG. So we have a sort of virtual MEG stereo signals that we can use to correlate and to compare the performances of the approach. About the method that we developed, we can divide it into 3 main steps. The first one, we develop a connectivity analysis on these 3 minutes of signal, and we applied. We will show here the results. Actually, we applied quite more, but we will show here the analysis of 2 index, the nonlinear regression index and the imaginary coherence. Why these 2 indexes? The nonlinear regression index is well assessed in the connectivity analysis of stereo EEG, and has the main advantage to be directed, so to have information about effective connectivity. And actually, we selected this after several tests because we saw that it was the main effective in support the localization of the epileptogenic zone. But this is not a good index when applied to MEG signals, so we also perform the same method with imaginary coherence when applied to MEG. Then the second step was extract indexes coming from, from graph theory. It is well known that the epileptogenic zone and the epileptogenic network are associated with those that can be called pathological hubs, that are region hubs that works in an altered and pathological way. So with graph theory, there are several and different metrics to calculate and to identify hubs that are the family of metrics belonging to node centrality. And we selected and we compare and we test different centrality metrics because since most of the time, most of the study of epileptic zone focus on one of 2, the most used is between a centrality. It is well known that this family of index are complementary. So here I put a very basic example of how 2 nodes can be central and can be hub with in 2 different ways. So in one case with very high degree, in one case with the lowest degree of the network, but with the highest between a centrality. So we consider that we need to combine in our approach different centrality properties that I resume here. These are the final 9 centrality indexes that we choose to apply, because I will not present for time here the results, but we saw that even if centrality is a characteristic, altered centrality is a characteristic of the epileptogenic zone, there is a strong between subject variability. I mean that each subject has some centrality alteration, but which kind of centrality different among subjects. So we decided to combine this family of indexes that with analysis we found was the most representative of this kind of variability. Then the first step was a machine learning classification. We applied supervised method of classification and a binary classification dividing into epileptogenic zone node and non-epileptogenic zone. And in order to test performances of the classificator, we consider the epileptogenic zone as defined by the clinical practice and intersected this region with the affected final resected area. And this was the gold standard that we used to assess the quality and the performances of our classification. A point that we on which we focused also was a specific characteristic of the classification part. That is that in this frame, we are working in the so-called imbalanced domain. That is that the two classes that we want to classify have a different distribution and a different numerosity. Especially the class that is most important for us to identify, so the epileptogenic zone, is the minority one. The problem of imbalanced domain is very, very well known in the community of machine learning analysis, but we also saw that in the application then of clinical studies, especially this aim of connectivity and localization of the epileptogenic zone is usually not considered. And so we made a study in which we also compare different family, and we take into account different family of approaches to take into account that the two classes that we want to classify are not the same size. And I will skip this detail, but I just put this slide to say that there is a huge family of methods to deal with the pre-processing of data in order to classify them. And we perform we perform a study in which we consider the parameters that we wanted to classify, that were the graph theory based indexes, and we test several methods of resampling, that are methods that take the indexes that we want to classify and perform a synthetic generating data or an undersampling of the data in order to create a sort of virtual data set to be classified that rebalance the two classes. And we test also the performances of these different rebalancing approach with a family of 10 different classifiers. And here we, after this study, we select just the best method. That is a method of oversampling in which we generated synthetic data, considering weighting in a different form the minority class examples, and we combine them with a classifier that also is not so used in this specific clinical domain, that is the ensemble discriminant analysis. In the ensemble classifier, the difference with the standard classifier is that we retrain. We can say that we do a sort of chain of training on the classifier, in which in each step we adjust the parameter of the classifier, improving the performances by removing those features and those examples that were not so well classified in the first step. So it's a sort of iterative steps that usually improve the performances of the classifier. And I stress this study because we saw that the difference between the original data, which whatever is the data set coming from connectivity and analysis, but the difference between the original data and the reprocessed data with the resampling approach is very huge in terms of performances, and is very is not so much applied as the difference of results stress. So this was the final pipeline of the method that we developed. So we select our stereo G and corresponding MEG signal. I try to resume the step of this procedure that we developed. The 3 minutes of epochs of connectivity analysis and their corresponding graph for each of these epochs. From the graph, we extracted the 9 complementary centrality indexes. And since the indexes belonging to the epileptogenic zone were less numerous than the other one, we applied a rebalancing producer to have the two classes enough balanced. And then we applied an ensemble classifier in order to choose and give the system to classify the epileptogenic zone or not, considering the epileptogenic zone as the intersection between those contact that clinician define as epileptogenic with, as in blue here, you can see the resected final area. So these are the one step that I forgot, sorry. And since we have not a so big number of patients, and we wanted this method to be patient-specific, we did a sort of cross-fold validation in which for each patient, we train the system with the information of the other n-1 patients. And then we, like if the other patient was the new information, we test with each individual patient. So we wanted to develop a system that was patient-specific. And these are the main results in which the same procedure was applied to both these results are only referred to stereo EEG localization, in which the two groups of seizure-free and non-seizure-free patients can be seen. What we can see is that the system was able to perfectly, almost 100%, so in 8 out of 10 patients were 100%, able to correctly localize the epileptogenic zone, only considering with these 3 minutes of inter-ictal signal, so more clean is possible. And was also able to localize the, with a percentage, with a rate of true negative of 60%. This means that we correctly localize all the epileptogenic zone, but the system classify as epileptogenic also another about 40% of leads that are not effective epileptogenic. The other data that we found, and that there was a clear difference between seizure-free and not seizure-free patients. Of course, we can't say exactly why a patient is not seizure-free. In this case, these patients, because but of course we can assume that there was a wider epileptogenic zone than one that was resected. And effective, our system found a lower true positive rate, so lower coherence or between the epileptogenic zone as identified by clinician and by our system, coherent with the non-seizure-free result of the patients. Then, to compare with the MEG results, we first focus on the seizure-free patients. And what we can see is that, unfortunately, there is in the virtual location of the MEG corresponding to the stereo EEG, there is not the same performances and same sensitivity in localizing the epileptogenic zone. So the same kind of connectivity and network information applied to the MEG is not able to localize as well as the stereo EEG performances. Since this study was done with the best connectivity indexes working for stereo EEG, that was the nonlinear regression index, we also repeat the same analysis with imaginary coherence, because of course nonlinear coefficient, for example, is very sensitive to volume conduction. So it's also obvious that its performances could be dramatically lower as it was in MEG signal. And what we can see here, we show that result, as we already showed for stereo EEG with nonlinear regression index, the MEG with the nonlinear regression index, and the same analysis with the same pipeline, but with the imaginary coherence. And what we can see is that it improved the performance in ability to localize the epileptogenic zone, so the true positive rate, but in the same time, it also decreased the true negative rate. So it like that through the imaginary coherence, much more zone seems to be identified as epileptogenic zone. So what are the main points of this procedure? That first of all, we have an automatic tool. This system is a complete automatic tool from the signals to the final classification that is able to identify the epileptogenic zone only considering short interictal signal. And is also patient specific, so it works for each single patient, and it's independent from the variety that we have of a zeta epileptogenic zone localization and epilepsy etiology. But this works very well in intracranial recordings, but had a clear lower specificity and sensitivity in inter-ictal network MEG analysis. That is the work in progress that we are trying to develop. So why this, and what are the open questions that we would like to propose and investigate with this preliminary study? Compare possibly different other approach of source reconstruction, and compare, since the signal are reconstructed in the same anatomical location of the stereo G, we could evaluate the effect of other approaches different than the basic that we use. The effect of source reconstruction models in the difference between the two signals. Change connectivity metrics. As we saw, changing from nonlinear index to imaginary coherence already changed the results. We can say for sure that, because we already did a lot of study, that for stereo G signals, because we compare several connectivity metrics, nonlinear regression index is the one who better in this kind of study localize the epileptogenic zone, but of course there is no direct relation with MEG signals. So in which way the different connectivity metrics relate with the two signals, we could further explore, and other graph metrics. And also but this is we still are in preliminary results. Correlate this data with distances among leads and see how anatomical distance influence MEG reconstructed signal and stereo G connectivity analysis. And also correlate with other zones, so not only a binary classification, but correlated also with more epileptogenic zone, like are the irritative and the propagation zone. That is the next step we would like to add to this methodological procedure. This is the network I would like to thank for the collaboration in this project and in this study, and that's all. Thank you very much.
Thank you very much, Giulia, for this very beautiful talk. Let's see if there are any questions from the audience. In the meantime, I actually have a couple of questions. The first one is, did I understand correctly, you work in the source space in this work, and you use individual MRI of the subjects?
Yes.
Because you say you were something really individual, but at some point you say that for the different subjects, often it was the case that different central measures were significant.
Yeah.
Did you try, like, for example, to see if, even though you do the whole procedure with the individual MRI, then you try to summarize it in some template? There are some quite standard tools to do this. So to go from the individual MRI and then to the template, to see in that case, if you then compute the centrality measure on the template, if this gives you more coherent results among the subjects. Did you try something like that, and did you think it has sense, something like that, something similar?
I don't know if I catch well your answer. I think that there is a small, or I didn't explain very well, that all the measurement of connectivity and centrality doesn't deal at all with MRI, because all the connectivity estimation and graph centrality comes from the estimation of the connectivity between stereo G signal and MEG.
Okay, so the connectivity is at the sensor level, not the...
You mean, sorry. No, it's at the source level. But when I told you that for each patient, different centrality combination better reflect the epileptogenic zone, I was talking about analysis performed of stereo G signal, because we first use stereo G as gold standard to understand the, let's say, the real network behavior. So we use stereo G to say which is the network properties that, since stereo G is really recording on the side, which is the kind of network topology that better describe inter-ictal epileptogenic zone. And then we try to see how much this fit with source signals, with source reconstructed signals.
Okay, I got it.
Of course, what we see is that the same procedure that is very strong in localize with stereo G, we just see that it's not so strong in MEG. So next step would be what you are suggesting. So try changes to understand why MEG source network behaves so different than stereo G network on the same location.
Okay, for this was my second question, because again, if I have understood correctly, stereo G measure something. Let's say if you want to measure a region, stereo G can really measure that region because they are really focal to that part, while MEG measure the whole brain.
Yeah.
From that point of view, does it make any sense to do some sort of channel selection before inversion? So you don't use the whole helmet, but for example, you try to select only the channel that really somehow measure the activity or the network that you want to reconstruct.
Yes, but I mean, in this, we were trying to put the question on the opposite sides, which is the influence of the sampling. That's why I proposed at the end that now we are trying to correlate this data with the distance between, because the sampling of the stereo G is not uniform. So we are trying now to correlate this data with the distance, and maybe the choosing of the sampling should or could come from the relationship between this centrality epileptogenic net values, how correlate with distances. But this is something that we just start to do, because otherwise, since we want to use this to localize, we should not have the a priori information of how to subsample the contact.
Sure. Okay. Thank you very much.
Thank you.
Let me check if there are other questions from the audience. Okay, if not, thank you again to Giulia. Really
Thank
much.
you.
Very nice talk.